Today we are going to do fractal sets. So what do we mean by that? So we mean complicated sets that are not simple like curves or patches of area. I will call these simple sets in ways that are intuitively clear. You may think of this as one-dimensional because you can use a curvilinear coordinate, for example, and find every point here. You may think of this as two-dimensional for similar reasons. Suppose you have a set that is actually two disjoint sets like this, but you are just looking at this combined set of points. This is still two-dimensional. There is no problem there. Suppose you have a curve here and a curve here and a curve here. This total set of points is still one-dimensional. There is no problem there. But for example, suppose I take this set. This is the Cantor's middle third or something. It is called like that. Middle third. The Cantor set. Okay, so what is the Cantor set? It is found as a limiting process. Okay, so we start with, let us say, a line like this, and we remove the middle third. So we get these two line segments, and then we remove the middle third of each, and then we get these four line segments, and then we remove the middle third of each, and we get, I'll draw that in yellow, so now we get two there, and two there, and two there, and two there, and we keep this going on and on infinitely many times. So we get, that's the Cantor set, that limit. Okay, what is its dimension? Is it one-dimensional? Is it zero-dimensional? What is it? Okay, so if I have 1 point here and 1 point here and 1 point here, these 3 points together, it's okay to call it zero-dimensional. But over here it does not seem that it might be zero-dimensional. It could be something else. Okay, so why do we even care about such a thing? So let's go to MATLAB for a second to remind ourselves that we might care about it in the context of vibrations. So here is the Duffing oscillator for the parameter values we have been studying, and then I can do things like set a tolerance, and then I can do things like start it with some random initial condition, let it run for a certain amount of time, and then I can say y0 is equal to, should it be x? Should be y. Okay, so so now that's, I've gone an integer number of forcing periods, and I've got enough time there in the simulation that transients can reasonably be called eliminated, and then this is a point on the attractor. This is a point which has reached its steady behavior, irregular though that may be. Okay, and then what I may do is I may define x as some blank set, and then I may go for let's see now. This command is okay. This I have already run. I will not run it now, but what I am doing is I'm going for many times. I'm going for some number of times in a loop. I am taking the end state as an initial condition. I am appending it to this set which is starting as 0. Then I am running it for one period. Then this is just a display, so that if it is a multiple of 500, I display k, and then I end it. So at the end of it I will have 50,000 such points. So let me just get rid of one of those 5,000 such points and just run it for a second to give you a sense of what is happening. This will take just a few seconds before a 500 pops up. Okay, so now I'm going to stop this because this calculation takes long, and here so far I have got 591 points. Okay, because even after the display of 500 it kept running. Then I have saved these somewhere, so let me say clear all and say load XX. Okay, so whose? I have 65,000 points here in X. Let me plot X1 versus X2 with dots, and we will see a familiar picture. You have seen this picture before. We have spent time looking at this picture. This is the Poincaré section, right? And as we have gone over it many times, when we look into it deeply, this has a complicated structure. Can we talk about the dimensionality of this set? That's the question. Okay, so let's come back here. So you can see that this Cantor set is a reasonable thing to think about when we are thinking of such complicated sets. So how do we define dimension for such a set? Okay, so we must find a dimension which, when we must find a method of computing a number which we will call dimension, which when we use it for regular sets like these will give integer numbers, and for those more complicated sets it may give fractional numbers. Okay, so the one of the simplest ones to understand is called the box counting dimension. So the way it proceeds is, let's say you have your complex set here. This is your set of points. Okay, in n dimensions. Okay, very good. Now somewhere in here it has complicated structure, it may have holes in it and so on, it doesn't matter. Now what you do is you come along and you take a region which includes all of these points, and then inside this region you divide the region into boxes of size or characteristic size epsilon. Okay, and then you see how many of these boxes have at least one point of the set in the box. So that is n epsilon is number of epsilon size boxes that have at least one point from the set of interest. Okay, how does this work out? So if you think about it a little bit, you will realize that this has very nice pleasing properties. So for example, let's say we are in 2D, but we are looking at this curve here. So what will happen is the slope makes a difference, but not much of a difference. What happens is I'll get boxes over here which will include points and so on, and all of these boxes over here will not include points. Okay, so what will happen is n of epsilon will be some geometrical factor c times epsilon for this curve. Okay, so if we think of n of epsilon as being more generally if n of epsilon is some constant times epsilon to the power m as epsilon goes to 0, then we say box counting dimension equals m, and it's easy to compute, right? Because what you do is you take log of n is equal to log of c plus m log oh, I made a mistake. this is minus m. Okay, so m log 1 by epsilon. Okay, because as epsilon goes to 0, n has to go to infinity usually. Okay, so so this is your box counting dimension. What happens is, if you take epsilon going to 0, this number becomes very big, this number becomes very big, this converges to some constant, and so what you do is you take the limit of epsilon going to 0 of the log of n of epsilon by the log of 1 by epsilon, and this limit is m. Now when you carry out this calculation with a computed set where there is a finite number of points, eventually your calculation will saturate because of data limitations, but before that you will get a nice scaling region. Okay, so that is the box counting dimension. You can see that it will work for a straight line or for a curve in 2D. What about in 3D? So if you are in 3D and you have a curve that looks like this, then once again you will have just boxes, only they will be cubes, right? And the total number will again just be, this is not correct, sorry, it is epsilon to the minus 1. Please correct that. Okay, so it will again be inversely proportional to epsilon. Okay, now let us move here to this part of the sheet and think of a patch, right? So let's say we have this patch, all the points are included, and we have this patch. These together are the set of interest. I make my grid and you can convince yourself quite easily that m will be 2 for this case. What about the Cantor set? So now the Cantor set, we can't look at the limit, but we can look at the limiting process. Okay, and we will choose a certain nice value of epsilon and see how it works out. So let us say this is the Cantor set construction. So we have 1 here, and then we have the next step, and then we have the next step. So we are constructing the Cantor set. Okay, and let us be a bit clever and choose this as the first epsilon, and what we are getting is n of epsilon 1 is equal to 2. Okay, then we choose this to be our second epsilon, and what we will get is n of epsilon 2 is equal to 2 times n of epsilon 1, while epsilon 2 is equal to epsilon 1 by 3. Okay, what this means is that epsilon k is equal to, let us say, epsilon 0 by 3 to the power k, and n of epsilon k is equal to some n0 times 2 to the power k, and therefore when I take the log of n of epsilon k, what I get is the log of n0 plus k log of 2, and when I take the log of 1 by epsilon k, I get minus the log of epsilon 0 plus k log 3. Okay, and then what does it mean for epsilon k to go to 0? It just means for k to go to infinity. So what I get is log of n of epsilon k by log of 1 by epsilon k, and I write in blue here to sort of simplify things a bit. For this I am interested in the limit as k goes to infinity. It is going to be the log of 2 divided by the log of 3, which we can calculate, and it is a number between 0 and 1, right? It doesn't actually matter whether you take natural log or anything else, right? By now you can, because you know properties of logs. So if you take common log of 2 by common log of 3, you get the same answer. Okay, we can find out this number in MATLAB quite easily. In MATLAB we can say log, that is actually the natural log, and you can see that it is 0.63. It is a fractional number between 0 and 1, that is the dimension. And we can also take log 2 is 0.693, as you may know, the natural number, but we can also take log 10 of 2, which is, you may remember, 0.3010. So if I take log 10 of 2 by the log 10 of 3, I still get this same number, 0.63. Okay, here 0.63. Okay, so that's the box counting dimension of the Cantor set. What is the box counting dimension of this set of points? We can only estimate it because we have computed it now. So what is the box counting dimension of this set of points? To do this, we have to write a program in MATLAB. Here is the program, I have written it now, and this is called boxdim2. I have worked it out in 2D only. As I have shown you, there are 65,000 points in there. What I will do is I will define an epsilon, an x range. So this xx, remember, has all of those x points, right? Whose is enough? X has 65,000 points with 2 columns. So when I take the minimum, x minimum is actually t1, but I will take it to be slightly smaller than that. EPS is just a tiny number in MATLAB, right? So I'll just take it to be slightly smaller than that, and y minimum is also similar. Okay, so then over here I can show you the min of x. It's basically minus 1.55 and minus 0.56. If you look at this figure, you will see minus 1.55 on this horizontal axis and minus 0.56 on the vertical axis. Similarly, the maximum is something like 1.57 and 0.4. When I come here and I do max of x, then about 0.4 and about 1.7. Okay, 1.7 in the y direction and about 0.4 in the x direction. Okay, so I have taken an x range by taking an x min and an x max, a y min and a y max. I have just increased the size of the box slightly bigger so that I don't start off with things on the boundary. Okay, now this n equals 11, I had run it earlier. I don't need that many. I will use n equals 10. Okay, so this is, you will see what n is very soon. Now over here what I will do is, for each of these n, I will take a dx. Now the dx I start with is the full range, so, and the dy is also the full one, x y max y minus y min. And what I will do is I will go from x min in steps of dx to x max. So when I start, I will just have x min and x max, because dx is the full range. Later you will see I am dividing it by 2, so then I will have 1, 2, 3, I'll have 2 boxes. Then I'll divide by 2 again, so I'll have 4 boxes. Then I'll divide again and I'll have 8 boxes, and so on. And since I've taken 10 here, 2 to the power 10 is a little more than 1,000, so I'll have more than 1,000,000 boxes, and I hope to get a good scaling range there. See, because after all I have only 65,000 points. I can't take billions of boxes, and of course it will also take a long time to calculate, and it may not be worth it. Okay, so let us remember, we expect the dimension of this set to be less than 2. it looks like a line, but it's a little bit fatter, but it does not seem to have any area. So we expect it to be less than 2, and we expect it to be a fraction, and there is a reasonable chance that it will be more than 1. Okay, but we will see. So now how does this program work? Once again, so I have chosen the x points based on the dx, then I'm taking the length of x points and the length of y points, and these should be the same, but I'm displaying just as a check, and then each time I start with s equals 0, and then I cycle through all the x points and all the y points, because they are boxes. That is why I don't want the last one. So if I have 1, 2 and 3 points, then I take the first point to define the first box, the second point to define the second box. Okay. Then if there is any x which is bigger than the lower margin of the box and smaller than the upper margin of the box, I keep equal here also, not here. And similarly, if there is a y that is bigger than the lower margin of the y part and smaller than the upper margin of the y part, if any, that means if any, what is any? Any is a MATLAB command. Let me just show you what that command is. So let us say x is equal to rand 3, 1. Any x will be 1. It says that it has a non-zero number. If I say x is equal to 0s, 22, 1, and if I say, so that's all zeros, right? If I say any x, it will give me 0. But if I say x 17 is equal to 0, 9 point whatever, something, now there is one number that is not 0. If I say any x, it will return 1. So there is a non-zero element. Okay. So over here what I am doing is, this is a logical process, right? Logical operator. So if there is any x point which is inside this box and inside that box, I have to have 1 here and 1 here and 1 here and 1 here. And if there is any such, then I will add 1. I will add that box to my count of boxes that have some number. And then that number n is going to be the sum for this box. And then I will do it again, and I will do it over all boxes. This is why I decided not to keep the 11, because it took some time, right? So that is 4 million boxes I'll be counting if I keep 11. But now I'll be counting up to 1 million. Okay. So this function returns two values, e and n. Let me save it just to make sure. Let me say en is equal to box dim 2. I don't have any input argument, so I don't have to say anything here, and I will get a display of this one, and I should just see whether the numbers are the same. I have done it, they are the same. You will see that the numbers are the same. And these numbers that we are getting are actually powers of 2 plus 1. You may notice that. So this will just take a little longer for the 500 and about 4 times that for the 1000. And I'm not keeping 11, so it will be over soon. Now, since the x range and the y range are not identical, I have to choose a size for the box. See, I have chosen rectangular boxes instead of square boxes, but it doesn't matter, right? I have chosen E to be dx, but dx and dy just have a constant ratio, because the boxes have a fixed aspect ratio. Okay, so this will just take a little bit of time, but not very long, and we'll get an answer soon. It's done. Oh, it was done. No, or it just got done. Whatever it is, it's done now. Okay. So let us now take log and 1 by E, because E is the size of the box, and N, and let's use circles and connect with a straight line for visibility. Okay, so here we are, and you see that as 1 by E goes to infinity, we get a scaling region. If I had continued it for far longer, eventually N would have saturated at 65,000, but I have not gone that far. I've got a good scaling region. And how big is the scaling region? The scaling region is, well, you know, if you just allow a little bit, in the beginning it's not quite nice, but from here at least 1.5, almost 2 orders of magnitude. If I do it with more points, I'll get a longer scaling region, but this is good enough for me. So now let me do the following. Let me say plot log of 1 by E log of N and I get basically the same graph, but the axes are real now, and they're not logarithmic, they're linear now. And then what I will do is I will say x equals g input, and I'll just select 2 points here. So let me say this point, by now it has sort of settled down, and this point is still in the scaling region. There are better ways to do it, but I'm just using a graphical pick-off over here. And then this number and this number are x coordinates, this number and this number are y coordinates. I am basically interested in the slope of the line. If you think it through, you will realize that is what I am interested in. So the x range is something like 2 to 5.5, and the y range is something going up to 9. You see that that is the case. And then what I will do is I will fit a straight line. Here is the x part, the first column, here is the y part, the second column. This is the order of the polynomial being fitted, which is a straight line, and it will give me 2 numbers, and the first one is the slope. So it gives me 1.24. Okay, so that is my estimated box counting dimension. With more careful numerics, I would be doing error bars on that and so on, but for here I am not doing that. So for roughing x double dot minus x plus x cube plus cx dot equals f sine omega t. This should actually be written here culturally, but I hope you will not mind my doing that. And then for parameters, here f 1.3, omega 0.6, and c 0.2. So f 1.3, 0.6, 0.2, my box counting dimension is something like 1.24. So you see it's a fractional number. It's a this is a that is what we mean by saying it's a fractal set. In dynamics we call it a strange attractor, because it has strange behavior. And to remind you, it is the dimension of this set that we have estimated. Okay, very good. Now there is another way of doing fractal dimensions, and that is called the correlation dimension. Okay, so let us do the correlation dimension now. So what is the correlation dimension? This one works really well in higher dimensions. See, I did the box counting in 2 dimensions, right? But suppose I have a 4-dimensional phase space, right? So to divide, to go from a box of size epsilon to epsilon by 10, I will have 10 to the power 4 as many boxes, right? So you can see that the box counting dimension in higher dimensions is terribly difficult, right? You need a very large number of points and a very long calculation. However, the correlation dimension is simpler, it's nicer, it works the same regardless of the dimensionality, and so I like this more for higher dimensional data, but I will demonstrate for this same problem. Okay. So as far as I know, the correlation dimension and the box counting dimension do not give the same result for fractal sets, or need not, but for integer dimensions they will be the same. Okay. So here this is how we will go. So let us say that I have this. Imagine that I have a 2D set, but of course I don't have the full set. I have points on it, some number of points, and let us assume that in this case they are uniformly distributed, right? So that means if I look at a patch here and I look at a patch here, the statistical distributions of points will look the same. Okay, this is different from our fractal set here, but I'm beginning just like this is, it's not uniform here, right? So you look here and there are no points here and there are points here, and you zoom in there and then you realize there are points here and points here, but the density here is more than here, and then you look there and you see that there is actually some other layering of that, and you will need a very large number of points to get a significantly clearer view of this set. But we will proceed with the idea that there is some finite large number of points over here. Okay, now what we will do, we will arrange is we will take all of these points x1, x2, I mean, you know, vector points, right? So these are states. So in an n-dimensional dynamical system, x1 will be n-dimensional, x2 will be n-dimensional, and so on. And then for some large number, right? And then what we will do is we will calculate distances. So what we will do is we will calculate x1 minus x2, x1 minus x3, all the way to x1 minus xn, and then we will calculate x2 minus x3, x2 minus x4, and then x3 minus x4, and so on. So we will calculate all pairwise distances, all pairwise distances. Okay, so from this collection of points we now have a collection of distances. I hope you can see that. So set of points, n of them, leads to set of distances, which is nc2, or n times n minus 1 by 2. This is sometimes written like this. Okay, so this many, so almost n square by 2 distances. So now you can see that if you have 1,000,000 points, then you'll have you know, almost 10 to the power 12 distances. But if you have 1,000 points, you'll have 500,000 distances. So for experimental work it is good, and we can easily work with 5,000 points, for example. Maybe not so easily with 65,000 points, but that's all right. So here we have these distances now. Okay, now the distances have a distribution. Okay, so now if you take any random variable, it has a distribution, it has a PDF, it has a CDF, and so on. This is the integral of that. This is f of x, x. It's a random variable. This is a probability density function, and this is the cumulative density function. What this is the integral of that. Okay, so now the empirical CDF of D, the distance points, can be found. Okay, how do you find the empirical CDF of a bunch of random numbers? So you plot the empirical CDF like this. I will run out of space, so let me be a bit careful and start this from here. Okay, so given scalar random scalar, because we've reduced it to distances. So from the vector which was n dimensional, we've gone to a scalar distance. That's why it's really very useful and good and simple. Okay, so given scalar random sample x1, x2, xn, what we do is we sort in increasing order. Let me say this is sorted. So you take a random sample, you sort it. So it's in increasing order. Then what I do is I plot this x here, and over here I have this scale that goes from 0 to 1. So over here I have xk, and over here I have a graph of k over n. This is called the empirical cumulative density function, and we will be interested in minor confusion. My fault. This is any random variable, and I was calling it x, but I've called the state vector x. So avoid confusion, let me now call this d1, d2 up to dn, sorted in increasing order, and let this be dk. Okay, so to help you realize that that's the scalar quantity. The scalar quantity is d. Okay, so we will be interested in how the distribution of distances of nearby points is. So we will be interested in the behavior of this empirical density function for small distances. Okay, how is that relevant? That's relevant because if over here what is the cumulative density function? So suppose I start a circle from here. Small circle, total number of points of distance less than the radius of the circle. Larger circle, total number of points less than the distance equal to radius of that circle. In this way you can see that if I take the cumulative density, it is related to the area of the circle. Now of course there are many such circles because I am looking at all of them, but for this set where they are uniformly distributed, I will get a dimension 2 when I look at this power. Okay, so let me call this f. What I will get here is f is like d to the power m, and for this uniformly distributed set I will get m equals 2. Similarly, if I have just some curve, then I choose this point, and within a distance epsilon I have a number of points proportional to epsilon, and I choose this point, and within a distance epsilon I have a number of points proportional to epsilon. Okay, so for this one I will get cumulative density is like d to the 1. For this one I will get d to the 2. There will be a constant here, but the constant does not matter. Okay, C0, C1, C2, who cares? We will get rid of it. Okay, when we look at the slope on log-log plots. So let us now do the correlation. Once again we will go to MATLAB. We will use the same set but a reduced number. So here correlation dimension X core test. I'm just loading something else. Okay, so here let me do this. Clear all, load XX, whose. So I have 65,000 points, right? Let me choose a random number times 60,000 and round that off. Okay, so there I've got 5,842. Okay, 52. All right. So what I will do is I will say X is equal to X 5852 to 10851. So I've taken 5,000 points. Okay, random points. Now they are not really random, they are generated by this dynamical process, but now I have to save it somewhere. Where will I save it? I'll save it in this xcore test. So I'll say save x core for correlation test, just because it's program, nothing, right? Just a name. So I've saved it there. Now that will be my input. Because I had written the program earlier with some q in mind, so I'm just saying q equals x. I'm looking at the size of it. I am going to return this vector e. That e has the distances in it. I'm starting with 0. Then what I will do is, while this size is more than 1, so obviously I'm starting with 5,000, it's going to be more than 1, right? What I will do is I will take out the first row and redefine the variable to be everything other than the first row. So I've left the first row and I've redefined the size. So next time it will be 4,999 and then 4,998 and so on. Okay, and I will be displaying this number. So when I run the program, it will run from 5,000 down to 1 or 0 or something, 1. And then over here what I will do is I will you see, now I have so when I start with 5,000, I have removed the first one. 4,999 distances are going to be there. So I am defining it to be zeros, and I am just taking the norm and getting the distance, right? And then I am appending this new set of m distances to the existing set, okay? And then I'll get this final large number. How many do I expect? I have size x, that's 5,000, so I expect 5,000 times 4,999 by 2. That is the number of distances I expect. Okay, now let me call it NE equals answer. Just we will look at it soon. All right, and then I say E equals CORRDIM, and now this m will run down from 5,000. Okay, so you see it running down, it will go to 1. It accelerates because the number of points is smaller as you go along. Okay, so there it is. And then I will look at the length of E, and that is the same as whatever I had called it. Now I've forgotten. NE. So NE and the length of E are the same, 1249750. That is what it is supposed to be. Now I will say E is equal to sort E, and I will say N is equal to 1 to NE by NE. Okay, so there I've got it now. And then what I will do is I will do log and E on the horizontal axis, N on the vertical axis. Now I will not use dots because I have more than 1 million points, right? I mean, I have 12.5 million points. I have a very large number of points. So here I go. And this is, of course, there's a very large number of points here. It makes no sense to plot 12 million points. Okay, so let me show you. So now let me say E is equal to E1 in steps of 100 to the end, and N is equal to N1 in steps of 100 to the end. And now I have 100 times fewer points, and then I can do another log, only plot this in red. And when I do that, you will see that the two curves are the same. It is only over here that there were very few points, so they got lost, but this entire part of the curve is the same. Okay, so let me close that now, and let me plot log of E, log of N. Okay, so here I have that now. Let me make that a bit bigger, and this is my scaling region, and you can see that it is a fairly large scaling region. Once again, I will use x equals, I don't want that, x equals g input 2, and then I will come here and I will try to select a reasonable scaling region. I will come here, there's still a bit of a bend here, so I'll come here and I'll come here. That's a reasonable scaling region. And then I will do polyfit. And you see now the slope is more, it's 1.2. Okay. So when I come here, I say I wrote it somewhere, but I'll just write it here. So for duffing with parameters as above, correlation dimension is 1.2. The other one was about 1.24. I admit that I have not done error estimates on it, but 1.2 and 1.24 are, I think, visibly different. So for example, let me go back to this curve here and let me take a range from -8 to 0. Okay, let me say C equals answer. Let me take Z is equal to -8, 0, and Z is equal to polyval. Evaluate the polynomial C at Z. Let me say hold on, and let me plot Z, Z in red. Okay, so this is our fitted line. You see it's more or less following the slope fairly well. Now let me say C1 is equal to 1.24. That was the other estimate, just to sort of let you see how sensitive it is. And let me say ZZ is equal to that again. And now let me plot this in green. And no, something is wrong. They can't be the same. No? That's because I did answer. C. So now I'll have to plot it in black or something. And you see that the slope does seem to be a bit different. So if we look a bit closer, you will see that the green lies along the blue better than the black does. The black distance over here is quite a bit smaller, over here it's larger. And so this is my empirical observation. Math proof maybe there is no reason to think that they are the same, but anyway, so box counting dimension is generally not equal to correlation dimension. This one is good for higher dimension, fewer data experiments. This is good. This one for some sets like Cantor, we can get very nice results. Okay, so that ends this lecture on sets with fractional dimensions or fractal sets and ways to define their dimensions. There are other ways of defining fractal dimensions, but I am not going to discuss them.